In the last paragraph at the end of the book, it said, some new ideas are here needed. And so there I was. Some new ideas were needed. Okay, so I started to think of new ideas.
Most brain activity takes place on the cell membrane of neurons. What happens here will help to uncover the secret of consciousness and deepen our understanding of how the universe operates. If we zoomed in and observed the microscopic world of particle interactions, we would see particles of all shapes and sizes constantly jiggling around and colliding with each other. Some pathways involve exquisite molecular machinery and elaborate particle choreography. For example, the beta subunit of ATP synthase turns ADP molecules and inorganic phosphates into ATPs. The ATP synthesis is driven by a rotating shaft. The rotating shaft is pushed by the bombardment of protons on the other side of the membrane. This process converts the proton gradient across mitochondrial membrane into an ATP gradient in the cytoplasm. The newly formed ATP molecules diffuse down their chemical gradient. When an ATP molecule bumps into the end site of a sodium-potassium pump, a transmembrane region opens up into the cell. This allows 3 sodium ions from the cytoplasma to enter the inner region of the pump. The entering of sodium ions cause a conformational change, breaking the phosphodiester bond of ATP and releasing an ADP. The conformational change opens up an extracellular gate, releasing the 3 sodium ions to the outside of the cell. In this ion-empty state, 2 potassium ions may enter the opening, causing the dephosphorylation of the pump, and followed by closing of the extracellular gate. This restores the pump's original conformation and allows the end domain to accept ATP again. The binding of ATP reopens the intracellular region and moves 2 potassium ions into the cytoplasm inside of a cell. The ADPs and phosphates released by the sodium-potassium pumps continue to bounce around. When an ADP bumps into the beta subunit of ATP synthase, a new cycle of ATP synthesis and sodium-potassium pumping begins. This process builds up sodium and potassium gradient across the cell membrane. The electrochemical gradient creates membrane potential. Maintaining the resting membrane potential accounts for the majority of a brain's energy consumption. Ion channels embedded in the cell membrane provide a passageway for charged particles to cross the membrane down their electrochemical gradient, counteracting the buildup of the electrochemical gradient generated by sodium-potassium pumps. Some ion channels are ligand-gated. The change in the concentration of a ligand opens or closes the corresponding ion channels. This effectively converts a chemical signal into a voltage signal. Other ion channels are controlled by the cross-membrane potential. For example, voltage-gated sodium channels allow sodium ions to flow back into a cell. Voltage-gated potassium channels allow potassium ions to flow out of a cell. When the disturbance of the membrane potential in a small region crosses a threshold, it opens many voltage-gated sodium channels and floods the cell with many sodium ions. This triggers a large change in membrane potential called an action potential. An action potential opens nearby voltage-gated sodium channels. The process becomes self-sustaining, resulting in an electrical signal that propagates from the cell body to the axon terminals. If we know the location and momentum of every ion and membrane protein in a brain, we should be able to calculate all the signal circulating in the brain, and hence deduce how it works. To accomplish such a simple task, we need to revamp the foundation of modern physics. We'll start with some basic concepts of quantum mechanics. Let Hp denote the action of an ion crossing, where P is a membrane protein, such as an ion channel, or an ion pump. The plus-minus sign annotates the direction of a microcurrent caused by the action of an ion crossing. Action H is annotated with a minus sign if the action results in a downward microcurrent. H- could be a positive ion moving down, or a negative ion moving up. Action H is annotated with a plus sign if the action results in an upward microcurrent. H+ could be a positive ion moving up, or a negative ion moving down. Previously, we discussed that all particles are created by actions. The action of an ion crossing creates a particle, which is equal to an ion crossing complex minus a standalone ion and a membrane protein. At first glance, this equation doesn't make any sense. If we subtract an ion and a membrane protein from an ion crossing complex, there is nothing left, and particle of H must equal 0. To understand why particle of H could be more than nothing, imagine that we live on an ion channel. We naturally choose the ion channel as our frame of reference. When we look around, we see ions bouncing around at the speed of a bullet. When an ion enters an ion channel, it slows down dramatically. When it exits a channel, it speeds up again. The average kinetic energy of a free ion is much greater than the kinetic energy of the ion as it passes through the channel. An interesting question arises. Where does the kinetic energy go when an ion crosses the channel? How does an ion regain its kinetic energy after leaving the channel? The issue is not specific to ion crossing. It's a phenomenon common to all particle interactions. For example, a stationary observer relative to a microtubule will notice that free kinesons are constantly jiggling around at high speed. But when they start walking, their walking speed is orders of magnitude slower than the speed of free kinesons. How can an enormous amount of kinetic energy disappear and reappear so quickly? Here is one possible explanation. The missing energy is trapped in the particle interaction complex in the form of mass. When the complex disintegrates, this mass is converted back into the kinetic energy of free-moving particles. An ion crossing complex is analogous to a neutron. When an electron is absorbed by a proton, they form a new particle interacting system called neutron. The mass of a neutron is greater than the mass of an electron plus the mass of a proton. A neutron can turn into an electron and a proton in a process called beta decay. During beta decay, the extra mass trapped in a neutron is released in the form of energy. In case you're not sure whether my statement is true or not, let's take a look at ourselves, a classical particle that we are all familiar with. We're made up of mindless particles. But none of the particles really belong to us. About 2/3 of our body mass is replaced every 2 weeks. All the atoms in our bodies are replaced every 5 to 10 years. The water molecules we exhale may join a new particle like a snowflake. Snowflakes wax and wane depending on the temperature and humidity of the environment. When the temperature rises, some water molecules will leave a snowflake and rejoin our body. What really distinguishes us from a snowflake is not those free-moving water molecules or their Brownian motion, but how they interact with each other. When they line up with their peers and form a beautiful pattern, they're part of a snowflake for the moment. When they are carrying nutrients and oxygen to a brain that appreciates the beauty of a snowflake, they are part of a human being for the moment. Both the human and the snowflake are ephemeral existences against a background of permanent Brownian motion. When a particle is observed at a sufficiently high spatial and temporal resolution, the boundary between that particle and its thermal environment becomes blurred. Subtract microscopic particles and their Brownian motion from a macroscopic object. What's left is a distinct pattern of particle interaction. The particle interaction uniquely defines this macroscopic object. In our discussion, we will use action and particle interchangeably. Let tau sub I be the observed time interval of an ion passing through protein P, and n be the total number of observations. Let tau be the mean of all observed time intervals. Given a mature and stable neuron, tau remains constant. Tau defines the natural unit of time for the ion passing through protein P. Let f be 1 over tau. F defines the natural frequency of the membrane protein P. It measures how often ions cross the membrane through protein P. All physical objects have a natural frequency. The natural frequency of an object determines how that object responds to different vibrations. Vibrating objects create signals. When a signal passes through an object, that object will resonate with the frequencies that match its natural frequency. This is a universal phenomenon known as resonance. Resonance is the physical basis of all neural processing. An object can retain some energy and continue to vibrate even after the original signal has passed. It is the physical basis for our memory. The oscillation of ion crossings on the membrane of neurons are the neural signals that circulate in our brain. They're the thoughts, dreams, all the feelings and emotions that ever pass through our mind. What you're seeing, and what you're hearing right now are the light and sound vibrations carrying my thoughts. When the light and sound signals reach the retinal cells in your eyes, and the hair cells in your ears, they're converted back to the oscillation of ion crossings on the membrane of your neurons. They're the signals carrying my thoughts in your brain. These signals interfere with the signals already circulating in your brain, creating unique patterns. That's how you form your own opinions and come up with new ideas. It is the similarity of our neural circuits that allows us to communicate with each other right now. The fine structure of our brain's frequency spectrum ultimately determines whether or not my ideas resonate with you. Let E0 be the change of potential energy as one elementary charge crosses the membrane. E0 depends on two factors: the cross-membrane electric field, and the height of the membrane. The cross-membrane electric field may fluctuate over time. But, in a mature and stable neuron, the mean of both values should remain constant. Therefore, E0 must also be constant. E0 defines the base unit of energy exchange for all ion crossings in a neuron. Let QE be the charge carried by the ions passing through protein P. The charge carried by a given ion can be either positive or negative. The amount of the charge is always an integer multiple of the elementary charge. Thus, QE must be an integer number. Let E be the base unit E0 times kh. E is the rate of energy exchange associated with the action of an ion passing through protein P. The relationship can be expressed as an equation. Energy E equals action h times frequency f. It's the same equation proposed by Einstein to explain the photoelectric effect. Rewrite frequency f as 1 over tau. Energy E equals action h over time tau. The formula can be interpreted as a definition of energy in a quantum system. Energy is the temporal density of actions executed by a quantum system. Let S denote the amount of action along a path. S is equal to n times h, where n is the number of ion crossings through protein P. N can also be expressed as time interval t measured in the units of tau. S equals h times t over tau. Rearrange the terms. S equals h over tau times t. Substitute h over tau with energy E. Action S equals energy E times time t. Energy and time are observables that can be measured in experiments. Action S is the number of ion crossing through P. So, we can deduce the number of ion crossings by measuring observables such as energy and time. In order to observe a complete ion crossing from start to end, delta t, the time interval of an observation, must be greater than or equal to the natural unit of time tau. Similarly, delta E, the amount of observed energy exchange, must be greater than or equal to the natural unit of energy, h over tau. What is expressed in the two inequalities is called the uncertainty principle. It states that there is a fundamental limit to what can be measured in a quantum system. The number of actions and all the observables derived from actions are undefined on a scale smaller than their natural units. It's meaningless to measure or talk about their values beyond this limit. We can transform the limit of measurement into a more familiar form. Both sides of two inequalities are positive numbers. It's okay to multiply both sides and make a new inequality. Delta E times delta t must be greater than or equal to 1 h over tau, times tau. The last two terms cancel each other out. The limit is expressed in an inequality similar to the one proposed by Heisenberg in 1927. Heisenberg recognized that quantum mechanics, as formulated by his generation, would collapse if it were possible to measure certain pairs of physical quantities, such as energy and time, or momentum and position, simultaneously with greater accuracy. So he proposed that it must be impossible. But Heisenberg didn't know a more basic mechanism from which the principle named after him can be deduced. In the context of ion crossings, it's easy to see why the uncertainty principle exists. A quantum system operates by executing one action at a time. That action is the fundamental unit of measurement for that system. All observables produced by a quantum system are derived from the unit action h. Time and energy are two reciprocal observables. Therefore, their product must be integer multiples of the unit action h. That's the origin of the uncertainty principle. Let lambda sub I be the observed displacement of one ion crossing through protein P, and n be the total number of observations. Let lambda be the root mean squared displacement of all ion crossings through protein P. When discussing the motion of walking kinesons, we define lambda as the arithmetic mean. That simplification is fine because we're only interested in one-dimensional motion along a microtubule. However, the motion of ion crossing takes place in three-dimensional space. The displacement in 3D space consists of the displacement along three orthogonal axes. The square of lambda is equal to the sum of the squares of lambda x, lambda y, and lambda z. That's why lambda in 3D space is not the arithmetic mean but the root mean squared displacement. Lambda z, the vertical displacement, is equal to the average height of the membrane protein P. The motion of an ion crossing along the axis perpendicular to the membrane is similar to a step taken by a kineson along a microtubule. It is a linear motion along a guide rail. Given a stable temperature T, lambda z remains constant. The motion of an ion crossing on the xy plane is very different from the motion along the z-axis. The lipid bilayer of the cell membrane behaves like a two-dimensional fluid. Unlike the guided motion along the z-axis, ion crossing complexes undergo random Brownian motion in a 2D space defined by the lipid bilayer. To calculate the mean displacement of ion crossing complexes, we need to figure out how far a Brownian particle travels in a given time interval. Fortunately, this problem was already solved by Einstein in one of his papers published in 1905. Let the density function ρ of x and t plus tau be the number of particles per unit volume around x at time t plus tau. The density around point x at time t plus tau must result from all possible sample paths around point x at time t for some random variable delta. ρ of x and t plus tau should be equal to the ensemble mean of all such paths taken around point x at time t, where psi of delta is the probability density of the particle changing its position from x to x plus delta in the time interval tau. Let's expand ρ of x and t plus tau as a Taylor series. The density around point x at time t plus tau is equal to ρ of x and t, plus tau times the first partial derivative with respect to time t, and plus other terms that are at least one order of magnitude less significant than the first two terms. Similarly, the Rig side of the equation can also be expanded as a Taylor series. By definition, the integral of the probability density function psi of delta is equal to 1. A Brownian particle should have the same probability of moving in the two opposite directions. So all odd moments of delta should vanish. The two identical terms cancel each other out. Eliminate all odd vanishing moments. As a first-order approximation, let's ignore the less significant terms in both Taylor series. We arrive at the diffusion equation derived by Einstein in his Brownian paper. Let d denote the coefficient after the Laplacian, the second moment of the probability of displacement delta. d is interpreted as the diffusion coefficient, whose value depends on the temperature and the viscosity of the lipid bilayer. Given a lipid bilayer at a stable temperature T, the coefficient d remains constant. Assuming that n particles start from the origin at the initial time t equals 0, the diffusion equation has the solution. The density ρ around point x at time t is equal to n over the square root of 4 pi dt times e to the power of minus x squared over 4 dt. The density function ρ is a bell-shaped distribution. Initially, the particles are centered around the origin. As time t increases, the distribution flattens, indicating that the particles are gradually moving away from the origin. Einstein pointed out that the mean squared displacement for a particle with initial position at the origin is equal to 2 dt. Lambda x, the mean displacement along the x-axis, is therefore proportional to the square root of the elapsed time t. By symmetry, lambda y, the mean displacement along the y-axis, should also be equal to the square root of 2 dt. Lambda xy, the root mean squared displacement on the xy plane, is the square root of the mean of lambda x squared plus lambda y squared. Thus, lambda xy is equal to the square root of 2 dt. The equation states that the mean displacement of a Brownian particle on the 2D plane is the same in all directions. Lambda xy is a function of the diffusion coefficient d and the elapsed time t. Given an ion crossing complex and a lipid bilayer at temperature T, both the diffusion coefficient d and the time interval are constant. Therefore, the mean displacement of an ion crossing complex from start to finish must be constant too. The same conclusion holds true for all particle interacting systems moving together in a three-dimensional thermal environment with various degrees of freedom. The root mean squared displacement of such a particle interacting system is a function of its thermal environment E, temperature uppercase T, and time interval lowercase t. Given an environment at thermal equilibrium T, the mean time interval of executing an action is constant. So is the mean distance traveled by the corresponding particle in that environment. Note that when we say that an observable is constant, we don't mean that every measurement of the observable results in a single and fixed value. Instead, what we mean is that when an observer takes a large number of samples and measures some physical quantity, such as the displacement or the time interval of a particular ion crossing from start to finish, the observed values have a stable probability distribution, and their means converge to a fixed value. Suppose that an imaginary observer can track ion crossing complexes in real time and measure their mean displacement without disturbing their natural motion. What would be the result of his experiment? Here is how we think of the problem. The displacement of an ion crossing complex results from a series of collisions. The displacement caused by a collision must follow some kind of probability distribution. The distribution can be expressed as a probability density function. Let the vertical axis be the probability density, and the horizontal axis be the displacement caused by a collision in a specific direction on the xy plane. A negative value means that a collision causes a displacement in the opposite direction. The exact shape of the probability density function depends on many factors, including the temperature of the environment, the mass and shape of the particular ion crossing complex, and how it interacts with its environment. Different ion crossing complexes may have different probability distributions. We have no idea on what the exact distribution of a particular ion crossing complex looks like. But, we do know that all ion crossing complexes undergo an enormous number of bombardments, roughly on the order of quadrillions of collisions per second. According to the law of large numbers, the total time interval of a large number of consecutive collisions should be equal to the expected value, or the mean time interval of one collision multiplied by the number of total collisions. Assuming that the mean time interval of a collision is stable, we can measure time by the number of collisions if that number is sufficiently large. For example, suppose that it takes an ion time tau to cross a particular ion channel or ion pump, and the ion crossing complex undergoes about 100 billion collisions per unit time tau. The total time interval of 2 billion collisions should be very close to 2% of the time tau. The distribution of the observed displacement in 2% of the time tau can be computed by taking out 2 billion samples from one of the distributions on the left, and summing all the sampled displacements. According to the central limit theorem, the sampling distribution should look like a normal distribution, even if the underlying distribution on the left is not normal. We just learned from Einstein that the mean of the distribution increases in proportional to the square root of the elapsed time, and that the distribution spreads out over a larger area as time increases. So the probability density function will move away from the origin and gradually flatten out. Let the horizontal xy plane represent the membrane of a cell, and the vertical axis be the probability density. At time t equals 0, an ion begins to cross the membrane through protein P at the origin. This surface shows the probability density of observing the ion crossing complex at different points on the membrane. The distribution starts as a Dirac delta function as an ion starts crossing through the protein at the origin. An ion crossing complex can move around in all possible directions on the two-dimensional membrane. Therefore, the probability density surface must be rotationally symmetric about the z-axis. As time t increases, the probability density propagates like a wave. When time t equals 1 tau, the peak of the probability wave travels the square root of 2 dt. If we were to track the motion of a particular ion crossing complex, we would see that it is undergoing random Brownian motion, and that its velocity changes with each collision. It's impossible to predict the exact position of a Brownian particle after billions of collisions. What is possible is to estimate the probability of observing a particle in a given region at a specific time. For example, after the time period of 1 tau, it's more likely to find an ion exiting protein P at the peak of the probability wave than anywhere else. The action of ion crossing creates a new particle, which is equal to an ion crossing complex minus a standalone ion and a membrane protein P. The particle of ion crossing is neither a free-moving ion nor a standalone membrane protein. It is a compound that encapsulates the action of a specific ion passing through a specific membrane protein. The particle of ion crossing is associated with a distinct time interval tau. Tau is the expected lifespan of that particle. The root mean squared displacement of this particle in the time interval tau defines its wavelength lambda. Lambda is the expected size of the space explored by this particle during its lifetime. Lambda and tau define the natural units of length and time for this particle. It's meaningless to talk about the natural behavior of this particle in a space smaller than lambda, or its evolution in a time interval shorter than tau. We'll use a unit circle to represent the lifetime of an ion crossing particle, and a rotating arrow to represent the unfolding of the action that creates the particle. If an action results in a downward microcurrent, represented here by a down arrow, we use the right-hand rule to draw a green rotating arrow along its path. The green arrow rotates counterclockwise when looking down from the z-axis. If an action results in an upward microcurrent, represented here by an up arrow, we draw a red rotating arrow along its path using the same right-hand rule. The red arrow rotates clockwise when looking down from the z-axis. Ion crossing takes place in a thermal environment. A particle of ion crossing undergoes constant Brownian motion. The position of that particle is best described by a probability distribution. The distribution should be close to a normal distribution, and the probability surface looks like a bell on a 2D membrane. The bump on the probability surface has the size of lambda, and lasts for the duration of tau. The action of an ion crossing is executed in a space the size of lambda within a time span of tau. If we follow the path of a particular ion channel or ion pump, we will observe a series of ion crossings. Each bump on the probability surface represents a distinct action of ion crossing. These particles share the same physical properties. For example, they have similar lifetimes, they explore the space of similar size, and exchange similar amount of energy during their lifetimes. Suppose that a distant observer tries to study the system with an ampermeter, and his ampermeter flashes a different color whenever it detects a unique ion crossing. He would see a series of flashes along the path, one flash per ion crossing. The flashes associated with the same ion channel would look identical to this distant observer. He would interpret a series of flashes as the same particle continuously traveling in space, just as a human observer interprets a beam of light as tracing the path of the same photon. But these flashes actually represent different generations of particles of the same lineage. A particle of ion crossing is analogous to a living organism like ourselves. Both have a finite lifespan, and both are made up of a specific pattern of particle interactions. The difference is that ion crossing complexes jiggle around on the membrane of cells, and living organisms wander around on the surface of the Earth. An ion channel is analogous to a strand of DNA molecules. When a strand of DNA molecules interacts with its environment, it produces generations of organisms which share the same physical properties. A line of organisms descended from the same ancestor would look identical to a distant observer who cannot examine the system up close. Similarly, when an ion channel interacts with its environment, it produces generations of particles which share the same physical properties. A series of ion crossings produced by the same ion channel would look identical to a distant observer who can only detect them as discrete events. The wandering organisms on the surface of the Earth leads to the evolution of species. The jiggling particles on the membrane of a neural network give rise to consciousness. No matter how drastically different these two systems may appear, their motion is governed by the same law that governs the motion of elementary particles. Let v denote the root mean square velocity of particles of ion crossing. V is defined as delta x, the distance traveled by particles of ion crossings, divided by the elapsed time delta t. Let lambda I and tau I denote the step size and time interval of a particle of ion crossing, respectively. Delta x equals the sum of all lambda I, and delta t equals the sum of all tau I. If n, the number of steps, is sufficiently large, the ratio of two sums can be expressed as n times lambda over n times tau, where lambda is the mean step size, and tau is the mean time interval. The two n's cancel out each other. V equals lambda over tau. Given a thermal environment at temperature T, both lambda and tau are constant. So the root mean square velocity must also be constant. The velocity is a thermal speed which is the same in all directions. We'll use the letter c to denote the constant speed lambda over tau. If a distant observer were to measure the speed of particles of ion crossing with an ampermeter, he would find that they were moving at a constant speed in all directions, independent of their initial motion. The result would look the same as the Michelson-Morley experiment. Let Ek be the mean kinetic energy of an ion crossing complex. The mean kinetic energy Ek is directly proportional to the temperature. Ek is equal to some constant k times the temperature T. Ek is equal to 1/2 mv squared, where m is the total mass of the complex, and v is the root mean square velocity. The total mass of an ion crossing complex consists of three components: the mass of the crossing ion, the mass of the membrane protein P, and the mass of one particle of ion crossing. Given a thermal environment, both the energy exchange associated with a given action h and its thermal speed c are constant. Thus, particles of a given ion crossing have a unique and well-defined mass. This formula expresses the mass-energy equivalence. It has the same form as that proposed by Einstein. The only difference is the speed c. In Einstein's theory of relativity, c is the speed of light in vacuum. In Einstein's world, the photon must enjoy a privileged status, and vacuum is different from any matter in the universe. In the supergeneral relativity, all particles are created equal, and no one gets special treatment. Photon is an ordinary particle created by the Planck action. Vacuum is an invisible thermal environment full of jiggling particle. The speed of light is just another thermal speed. Since the speed of light in a vacuum is the ultimate speed, vacuum must be the hottest and most energetic object in the universe. This explains all the missing dark matter and dark energy, and why the universe may undergo thermal expansion. Suppose there is a mechanism at the origin, and that this mechanism keeps emitting ion crossing complexes. A distant observer tries to study the system with an ampermeter. Because of the distance, the whole system looks like a point particle to him. He cannot directly observe its inner workings. This observer has a supersensitive ampermeter, which can detect the microcurrent of a single moving charge. When he turns on his instrument, he always sees something like the old TV static. The flickering dots are caused by an enormous number of charges bouncing around in the environment. But the observer thinks they're just white noise and carry no useful information. He uses various techniques to eliminate the flickering dots, which he considers random noise. After careful data processing, he's able to see distinct flashes on a pristine background. Just like a human physicist studying elementary particles from a great distance, this distant observer believes that each distinct flash correlates with the detection of a unique particle. As an observer who can look closely at the system, we know that what he detects is neither a free-moving ion nor a membrane protein, but the action of a particular ion passing through a particular membrane protein. The distant observer discovers that in order to observe a distinct flash, the time interval of his observation must be greater than or equal to 1 tau. Otherwise, the signal becomes indistinguishable from background noise. He also finds that it is impossible to determine the exact position of these flashes. At time t0, most of the flashes are centered around the origin, and they are randomly distributed in a region about the size of lambda. The observer decides to use a probability density function to describe the initial position of the particles observed at time t0. At time t1, he observes flashes everywhere, and spreading out from the origin. He collects a large number of samples, and constructs a probability density function for the position of the particles observed at time t1. The peak of the probability density travels the distance of 1 lambda in the period of 1 tau. He repeats his experiment, and constructs a probability density function for the position of the particles observed at time t2. A series of density functions forms a probability wave propagating from the source at the origin. The probability wave has the wavelength of lambda and travels at the speed of lambda over tau. From a distant observer's point of view, it appears that particles radiate from the source at the speed of lambda over tau. As far as he can tell, if a particle is observed to move from position A to position B, that particle must move continuously in a straight line to position C. However, if we look closely at the motion of ion crossing complexes, we'll find that the particles never go straight from A to B, and then to C. Instead, the particles jiggle around randomly. At first glance, they don't seem to be moving in any particular direction. If we superimpose many paths that start at A and pass through B, they form a density cloud. The density of Brownian paths travels at the speed of lambda over tau from A to B and then to C. It propagates like the probability wave observed by those who can only detect ion crossings as discrete events. They're essentially the same density function, differing only in spatial and temporal resolution. Therefore, we can calculate the probability of observing a particle from one point to another by summing all possible paths between 2 points. This is the approach used by Feynman in his path integral formulation of quantum mechanics. But Feynman probably didn't realize that the thermal environment is an integral part of a quantum system, and that his formulation could be deduced from this simple mechanism. Quantum mechanics describes system behavior by aggregating all possible paths of evolution. Classical mechanics focuses more on local behavior and the rule governing the motion of individual paths. The aggregate behavior is usually different from the individual behavior. In our daily lives, we experience the classical world because we can't see the forest for the trees. When we study the microscopic world, we always see the forest and never the trees. That is why the quantum world seems to behave so differently. Here is another unsolved mystery in physics. The flashes seen by a distant observer result from particle interactions. An action involves 2 or more components. All the components undergo constant Brownian motion. None of the components really has control over their motion. An action, like a life, is largely a coincidence. None of the participants can plan their role in an action beforehand. After their role has ended, all the participants disperse immediately, and keep bouncing around in all random directions. No one remembers what they were doing before. No one knows what they're going to do next. However, if we follow the ion crossings that start from A at t0, and pass through B at t1, we'll find that they seem to continue moving toward C. As random as they might look, most flashes observed at t2 spread around C, and few go back to the area around A. They show a strong tendency to keep exploring new territory, and know how to avoid the area that they have just explored. If we move the source of the ion crossings to position C, we'll see the same pattern, but in the opposite direction. We can repeat the experiment in any orientation, we'll get similar results. What happens in C at t2 is always coupled to what happens in A at t0. One might say that the 2 separate events are entangled. If we compare the ion crossing complexes in A, B, and C, they look similar, but they're not made up of the same set of identical ions and membrane proteins. So the participants of each ion crossing observed around C would have no idea what happened in A at a previous time. How could they possibly know to avoid the area around A? The answer lies in the environment. The execution of an action must involve some kind of energy exchange. In the case of ion channels, ions flow down their electrochemical gradient. The electrochemical gradient is a form of potential energy. Ion crossings reduce the electrochemical gradient, and convert the potential energy to the kinetic energy of the crossing ions. In the case of ion pumps, ions are pumped against their electrochemical gradient by ATP hydrolysis. This builds up the electrochemical gradient, and converts the chemical energy to the potential energy. A complete cycle of ion crossing consists of a pair of actions and counteractions. One is an ion flowing down its electrochemical gradient, and the other is to pump that ion back and restore the gradient. The evolution of the system is the repeated execution of this ion crossing cycle. For each cycle, one ATP molecule is split into one ADP and one inorganic phosphate. The electrochemical gradient remains unchanged. A pair of action and counteraction defines a pair of particle and antiparticle. To a distant observer like Dirac, a pair of particle and antiparticle always annihilate each other, releasing energy in the form of particle radiation. In the process, a Brownian particle turns into two Brownian particles. This increases the entropy of the system. The monotonic increasing of the entropy defines the arrow of time for the evolution of the system. The evolution of a physical system must be powered by some kind of energy. Thus, the energy is always tied to the progress of time. The rate of energy exchange defines the energy state of the system. The energy state is the temporal density of the actions executed by a quantum system. Its natural unit E is equal to the unit action h divided by the unit time tau. When the evolution of a quantum system unfolds in space, it exhausts local energy supply and creates an energy gradient. This effectively breaks space symmetry. The breaking of space symmetry gives the system a direction in its space evolution. It's why ion crossings have the tendency to explore new territory, and avoid the space that they've just explored. That tendency defines an observable called momentum. The natural unit of the momentum p is equal to the unit action h divided by the unit length lambda. The momentum p is a vector quantity. Its direction points in the direction of the largest increase of energy. Its value is equal to the spatial density of the actions executed by the system. Space, time, momentum, and energy are observables describing different aspects of the same action. If we look at an action through the lens of time, we see the exchange of energy. If we look at the same action through the lens of space, we see momentum. No matter how complicated an action is, its execution is always transactional. In a transaction, the total amount of credits is always equal to the total amount of debits. This is why energy and momentum are always conserved in the universe. A quantum system has to operate in a thermal environment. The shared environment connects distant events. It's a simple mechanism that underlies all quantum entanglement. To an observer who cannot see the shared environment, a local event appears to be mysteriously entangled with a distant event. To an observer who can see the shared environment, it's obvious that some global states are encoded in the structure of spacetime. There is nothing mysterious about the entanglement of two separate events. Let F denote the unit action h divided by the unit time tau and the unit length lambda. F is a vector quantity pointing in the direction of the displacement of an action. H over lambda is momentum. F equals momentum p divided by the unit time tau. F represents the temporal gradient of momentum. Similarly, h over tau is energy. F equals energy E divided by the unit length lambda. Thus, F also represents the spatial gradient of energy. Let's take a look at this formula. F is equal to energy E over lambda. Energy E is equal to mc squared, where m is the mass of an action, and c is the thermal speed of that action. The thermal speed c is defined as the wavelength lambda divided by the unit time tau. Cancel out 1 lambda. Fh equals the mass m times the unit length lambda over the unit time tau squared. Fh defines the natural unit of the force exerted by an action. Let Fn be the apparent force experienced by a classical object, where n is the number of microscopic actions acted on the object. Fn is equal to the sum of all the unit forces. Note that the unit forces are vectors pointing in different directions. To add them up, first substitute Fh with the formula on the left. Fn equals the sum of m times displacement lambda times tau squared. Both m and tau are scalars. For the same action, m and tau are two constants. We can move them out of the summation. Fn is equal to mass m times the sum of individual displacement lambda over tau squared. The sum of individual displacement lambda is the displacement of the center of mass. Let dx denote the displacement of the center of mass. Displacement dx divided by the unit time tau squared is the second derivative of displacement with respect to time. The second derivative of displacement defines the acceleration of an object. The equation expresses Newton's second law of motion. The acceleration points in the same direction as the force. Its magnitude is directly proportional to the magnitude of the force, and inversely proportional to the mass of the object. Thus the law of Newtonian physics is derived from the principle of quantum physics. The sum of all actions approach treats all the forces in the universe equally. No force is more fundamental than others. This is how all of the different forces in the universe can be unified. To see how a macroscopic force is born out of microscopic actions, let's look at the motion in a live cell. During mitosis, all the chromosomes are lined up in the center of the cell. When the right signal comes, the chromosomes are split into two sets of identical chromosomes. The two sets move in the opposite directions. This causes one cell to divide into two. To a macroscopic observer, the motion of the chromosomes must be caused by some kind of force. After mitosis, the force must have disappeared because no apparent motion is observed. To a microscopic observer, the chromosomes are just passive cargo. The observed motion is caused by a large number of discrete walking actions. During mitosis, many microtubules line up to form parallel bundles. When motor proteins walk along these microtubules in synchronization, the microscopic actions add up, resulting in the apparent motion of chromosomes. Both motor proteins and microtubules are long-lived proteins. Whenever they bind to each other, they continue to interact and produce walking actions. So even if a cell is not in mitosis, the system still consumes about the same amount of energy and produces about the same number of actions. But these actions no longer form any particular pattern. A large number of random actions tend to cancel each other out. The system doesn't output any observable motion at the macroscopic level. To a distant observer like Newton, no apparent force can be observed, and the whole system looks like as empty as a vacuum. Let's recap what we've learned so far. A quantum system contains an enormous number of jiggling particles. These particles provide a thermal environment in which the system operates. The thermal background is usually invisible to a distant observer. Typically, an observer can only probe quantum systems through discrete events. Each event corresponds to the execution of a particular action, which is often interpreted as the detection of a unique particle by that observer. An action consists of a series of particle interactions that define a quantum system. All the observables produced by the system are derived from the unit action h. That action is the fundamental unit of measurement for the system. Space and time are not abstract constructs. They are physical observables resulting from particle interactions. There is no absolute ruler or clock in the universe. Let tau be the mean time interval of the execution of a complete action. Let lambda be the root mean square displacement explored by that action. For a given thermal environment, both tau and lambda are constant. Tau and lambda defines the natural unit of time and length for the system, respectively. The inverse of tau defines the natural frequency of the system. The natural frequency determines how the system responds to vibrating signals. The execution of an action must be powered by energy. Energy is usually supplied in two forms. One is potential energy, which is essentially a particle gradient. The other is stationary energy, which is kinetic energy trapped in a confined space. In the case of ion crossings, the energy exchanged in an action is equal to some basic unit E naught times an integer q, where q is the number of elementary charges carried by a passing ion. The evolution of a quantum system consumes energy, which causes the monotonic increasing of entropy. This gives rise to the arrow of time for the evolution of the system. As evolution unfolds in space, the local energy supply and demand is temporarily out of balance, breaking the symmetry of space. This creates the momentum for the system's evolution in space. H over tau defines the natural unit of energy. H over lambda defines the natural unit of momentum. And H over tau and lambda defines the natural unit of force. Let S be the number of actions along a path traveled by an ion channel or an ion pump. S can be expressed as the unit energy E times t, where t is the total traveling time along the path measured in units of tau. S can also be expressed as the unit momentum p times x, where x is the length of the path measured in units of lambda. We can calculate the number of actions executed in a system by summing up the actions along all paths. It is the basis for Feynman's path integral formulation of quantum mechanics. Any measurement of a quantum system must observe the execution of at least one action. Therefore, the product of two reciprocal observables must be greater than or equal to one unit of action h. It is often expressed as delta E times delta t is greater than or equal to 1 h, or delta p times delta x is greater than or equal to 1 h. This is commonly known as Heisenberg's uncertainty principle. An action defines a particle. The lifetime of this particle is tau. The size of the space explored by this particle is equal to lambda. Let c be lambda over tau. C measures how fast particles explore their environment. As a quantum system evolves, different generations of the same particle spread out like wave. They continue to explore the neighboring space in the direction of the greatest increase in energy supply. The particle wave travels at a constant speed in all possible directions. Its speed is independent of the motion of the source or the motion of an observer. The same mechanism underlies the constant speed of light, one of the central postulates of Einstein's special theory of relativity. Let m be the unit action h times tau divided by lambda squared. M defines a scalar observable on the unit action when viewed through the combined lens of space and time. Let's divide both the numerator and the denominator by tau squared. The numerator becomes h over tau, which is equal to the natural unit of energy E. The denominator becomes lambda squared over tau squared, which is equal to speed c squared. We have just derived Einstein's mass-energy equivalence equation. Thus, m must be as the inertial mass in Newtonian physics. When two or more Brownian particles interact in a thermal environment, they'll form a complex that persists in the environment for a period of time. Some of the kinetic energy is trapped in the complex in the form of mass. The mass m times the thermal speed c squared quantifies the average kinetic energy trapped in the complex. In a stable system, the number of actions must equal the number of counteractions. In other words, particles and antiparticles are always created in pairs. In classical mechanics, only one side of that pair is observed, and the inertial mass of that pair is assigned to one particle. That's why Ek, the kinetic energy of a particle in classical mechanics, is equal to 1/2 of the classical mass m times its speed c squared. Just as space and time are not absolute, temperature is not absolute either. There is no universal thermometer for all particles. Even if two particles share the same reality, they may not experience the same temperature. For example, to a human observer, outer space feels super cold because all the forces acting on their heat sensors are almost perfectly balanced. However, to an observer the size of a photon, outer space must be super hot because they're bouncing around at the speed of light. The apparent temperature experienced by a particle is proportional to its average kinetic energy. Therefore, we can use Ek to measure the temperature of that particle's thermal environment. A moving charge generates electric current and voltage. The action of ion crossing produces a microcurrent perpendicular to the membrane. Its magnitude I is equal to the unit charge q divided by the unit time tau. The voltage across an ion channel or ion pump is equal to the energy E divided by the charge q. Replace E with h over tau. The voltage V is equal to h over q and tau. The resistance across an ion channel or ion pump is equal to V over I. Replace V and I with the values expressed in natural units. The resistance R is equal to h over q squared. All observables are now expressed in natural units derived from the fundamental unit action h. Thus, in principle, all observable behavior ever produced by a brain can be understood by counting actions. For example, if we can count the number of actions in a given region at a given time, we can calculate the membrane potential in that region, and derive all the neuronal firings in a brain. We can also calculate the momentum of all the ion channels and ion pumps, and all the forces acting on them, and infer how the system works. But this is not a trivial counting problem. Our brain expresses hundreds of variants of ion channels and ion pumps. There are about 100 billion neurons in a brain. About 1 million ion channels and ion pumps are constantly jiggling on each and every neuron. These neurons make an average of 10,000 synaptic connections to their neighbors. Together they form an unbelievably complicated membrane structure. We won't live long enough to count all the ion crossings in our brain, let alone track their movement and interaction. We have to find some shortcuts in order to make sense of the universe and our own existence. If you find the content in this channel is interesting, please click the like button below, subscribe, and share it with your friends. It will help to connect those who are also interested in the topic. Thank you very much for your help.